In this video, we begin our discussion finally about how to establish the derivative, which is associated with slopes of our curves or instantaneous rates of change. Again, we've had plenty of discussions about it, so now we're going to finally get down to brass tacks. We've built up our understanding of infinitesimals, how to go from hyperreals to the reals using the standard part. So we finally have all the machinery ready to go to finally define what we mean by the slope of a curve or the instantaneous rate of change, or again what we'll call the derivative. So first off, let's remind ourselves and review lines, one of the most basic geometric objects we have. So here is the graph y equals 3/2 x plus 1. So you recognize that's in slope-intercept form, and so we already know that the slope of this line is 3/2. And just to reiterate, what does that mean? Well, if we start at some arbitrary point, in this case 2, 4, and with a slope of 3/2, if we go over in the x direction 2 units and go up in the y direction 3 units, we end up right back on the line. And in fact, it doesn't matter where you start, any place on the line, if you go over 2 units and up 3 units, you arrive on the line, which is why we say the slope of the line is 3/2. It's the ratio of the change in y over the change in x. Now, if we look at a curve that isn't a line, say this parabola right here, hopefully you understand that no one ratio is going to work to talk about the slope of this curve. This slope, however we could define slope, is going to be different for different points. However, and this is exactly where infinitesimals come in, almost or exactly every single one of the curves we study in this class, when you look close enough, it'll look an awfully lot like a line. So let's take, for instance, this point here, 2, 1. So if I zoom in at the point 2, 1 and keep zooming in, I can still see there's lots of curvature, but it's straightening out. And as I get way in, almost, let's say, I don't know, this is probably far enough. At this point, we can see that it's very linear. Same curve. I just zoomed in, but now look at our scale. From here to here is 10 to the negative 1, or 2, sorry. So it's 0.001 or 1/100th. So our units are really small. But now I can approach this just like I would a line. So for instance, I can go down 0.004 units. Now it's very small because of our scale. And go over 0.002 units. And notice I'll still stay on the curve. And so we can look at that and say, well, let's say that this is going to be an approximation of our slope. And so the slope, our change in y over change in x, just like in the line, would be the ratio negative 0.004 over 0.002, which is negative 2. Now, this has to be an approximation, because even though on this picture it looks like I stayed on the curve, if you truly put in those two values, you would find out that you're not quite satisfying the parabola anymore. But nonetheless, I can think of this as a line. In fact, I can plot the line that goes through this point and has slope negative 2. I'll plot it right now. Whoops. And we see that it matches our graph perfectly at this incredibly zoomed in scale. But of course, if we zoom back out again, get more to a more normal scale, say our original one here, then we can see that the line only agrees for a mere second and then disagrees with our curve from there on out. So that's a visual representation of what we mean by the slope of the tangent line. But now let's get into formally defining what we mean. So now we look at how to compute algebraically the slope of a curve using infinitesimals. So the equation of the curve we had before was y is equal to negative x minus 1 quantity squared plus 2. Whoops, minus 1. And so we let delta x be an infinitesimal. So delta x is some infinitely small number. And we're going to add it to 2 because we're looking at the point 2, 1. So let's first off look at at the point 2, 1, we'll see that the change in y, the infinitesimal change in y, will be negative 2 plus that infinitesimal, so 2 plus delta x, minus 1. So right here, where we had the x, that's getting replaced with 2 plus delta x. And of course, we add, that whole thing is squared, we add 2. So that's the new point, and we'll subtract from it where we began. So minus 2 minus 1 quantity squared, it needs to be the whole thing, plus 2. So working this out algebraically, we see that this is equal to negative, the 2 and the 1 become a 1, plus delta x quantity squared plus 2. And then here we have 2 minus 1, which is 1. There's a negative in front of there. So that's 1 squared minus 1, so that becomes minus 1. And then this, expand this out, we get a negative 1 minus 2 delta x minus delta x squared. And we can simplify here. 2 minus 1 is 1. And now continue to work out the algebra. The 1's cancel out, and what we get left behind is simply negative 2 delta x minus delta x squared. So that's what the change in y is, right? That's what we just calculated here. The change in y, if we do this infinitesimal movement of delta x, then y changes this much, negative 2 delta x minus delta x squared. That's the change in y. So then slope will be the standard part of delta y over delta x. So slope of y at the point 2, 1 will be given by slope is equal to the standard part of delta y divided by delta x, which we now know is the standard part of negative 2 delta x minus delta x squared. That's the change in y part, and delta x is our change in x. And this is equal, we can cancel out, we go delta x is everywhere, so this is equal to the standard part of negative 2 minus delta x. And since delta x is an infinitesimal and negative 2 is a real number, the standard part of this is just simply negative 2. Which is exactly what we saw when we investigated that curve. When we zoomed in really small and we moved off by a small amount, remember we adjusted by 0.002, that was our delta x. So in terms of graphics, that's pretty small level, though not an infinitesimal, that is a real number. But nonetheless, when we use that small number, up to the whatever error we had, it was close to negative 2 plus or minus something. But now we can see when we go to the land of infinitesimals for real, things that are infinitely small, if we make an infinitely small adjustment to y and look at the ratio of the change in y over change in x, we get exactly that the slope is negative 2.